We are going to start today with a workshop. I'm afraid I've forgotten the exact name. Something like industrial applications and numerical applications of aeroacoustics. It's something along those lines. And our first speaker is Christophe Schram, who is a very experienced person in aeroacoustics and also very experienced with running RTAs. Your last one was Smart Arts?
Zephyr. Since then there has been Zephyr, so that makes 3.
Wow, that makes 3.
Yeah, there's too many of them.
We couldn't wish for a better first speaker. Christophe's talk is on Introduction to Acoustic Analogies.
Thank you very much, Maria. That's for a very kind introduction. Welcome. So, of course, I join myself to Maria for the pleasure that we have to be in flesh, standing in this room, and the pleasure that I have to teach to all of you, or to present this. So this is an introduction to acoustics and acoustic analogies in particular. So that's something that will look familiar for a number of us to a number of you, but this was meant to be a nice introduction. Well, nice, let's go. This was meant to be an introduction for the next courses, the one of Sophie Lebras in particular, who will spend more time on the more practical application of acoustic analogies, then Adrien Berriot, who will considerably enrich the discussion on the acoustic propagation side. Someone is not muted. So, Alice? Okay, that's good.
Hi.
Yeah, someone is not muted. If I may just kindly ask all participants to mute their system. Someone is having breakfast. So, yes. So Sophie, you have the possibility to mute people. That's right. Okay. So yeah, so welcome everybody. So let's go directly to the table of content of this presentation. So this is the plan of the discussion. Well, before anything else, don't hesitate to interrupt. I mean, I like being interrupted because it makes the thing more lively and more entertaining, hopefully. So this is the plan of the presentation. So we'll start by reminding how you derive acoustic propagation equations from the equations of fluid mechanics. And that proceeds by linearizing the conservation equations, and then we end up with linearized sources of sound, which are not going to tell us a lot about turbulence, because when you linearize Navier-Stokes, you throw the baby with the water of the bath, as we say in French, so you discard the turbulence. So if you want to predict the noise emitted by turbulence, you need to non-linearize, actually, to not linearize the equations of fluid mechanics, but you will see that Lighthill's analogy proceeds very much in the same way than when you linearize the conservation equations to form a wave propagation equation. So this time we will retain the nonlinear sources of sound and notoriously the turbulence. Then we'll make a quick digression on the choice of the acoustic variable, because you guys are more busy with thermoacoustics, as far as I understand, and we will see that for thermoacoustic problems, some acoustic variables are more suitable than others. And then we will end up with a nonlinear, with an inhomogeneous wave propagation equation that we would like to solve. Okay, and there are different methods for solving those equations. What we will use is the formalism offered by Green's functions that will lead us to an integral solution. And then we will argue that integrating is good for health. And that should be clear, hopefully, by the end of the course. And then while we are busy with Green's functions, we will talk about free field Green's functions and tailored Green's functions, and a particular variety of tailored Green's functions is for duct acoustics, which I thought would be relevant for you because combustors are essentially pieces of pipes, right? Well, with perforations, but still looking a little bit like pipes. And then we will go on to Kerr's analogy, which is an application, which is a resolution of Lighthill's analogy when you don't have a tailored Green's function at your disposal. And then we will mention some things about acoustic energy, and hopefully, if time allows, with a small demo of the Reg bazooka that I have here, courtesy of Miko, who's sitting in the back. And we will see how the acoustic energy equation can already provide a lot of insight to explain why this animal in here might be resonating or non-resonating, depending on the position of the grid. Any questions on this? Is this suitable as a menu for this morning? Something you regret not seeing? Well, anyway, it's too late, but you can always ask. Okay, so just a very quick reminder through the Navier-Stokes equation that, okay, of course, basic material, but it's just to get along with the notations that we have here. So we have the continuity equation that states that the rate of change of the density of a fluid particle moving with the fluid, so this is a material derivative, is caused by a dilatation. Then we have Newton's law, F is equal m times A. Okay, so the mass of a fluid particle times its Lagrangian acceleration is the result of forces being applied to the fluid particle. And those forces are going to be the hydrostatic pressure and the viscous stresses and body forces, like in this case would be the gravity field or an electromagnetic field. And if I simply substitute this into that, then I end up with this form for the momentum conservation equation. And then what we are going to do is to simplify those equations, because solving those equations would effectively give you the acoustic field, but it's a very complicated way to solve the acoustic field. There are smarter things to do, and Sophie, in her course, will elaborate on why the acoustic quantities are typically small quantities, and because the acoustic quantities like the density perturbation, the pressure perturbation, the velocity perturbations are small quantities compared to those that characterize the flow or the atmospheric pressure, for example. This will allow us to linearize the equations, and then it will considerably facilitate our task to obtain the acoustic field from those equations if we proceed through a priori linearization. So that's what we do. So we have just rewritten the equations in here. We have a source term in here and the equation of mass that is a little bit artificial, but that translates the effect that an injection of mass would have as an equivalent source of sound. Okay, it will allow us to illustrate the monopolar character in particular of this guy here. So I have the Navier-Stokes equations. I introduce my decomposition between mean, uniform and average quantities, uniform and constant quantities by the subindex 0 in here, and the perturbations. And because we deal with acoustic propagation in the medium at rest, the mean velocity is 0, 0. So that's the main difference with respect to what Adrien, for example, will present. So Adrien will include the possibility for the acoustic waves to be carried away by the flow and all the associated effects in terms of acoustic refraction and convection. Okay, so in this framework, we describe acoustic propagation like in this class, right? There's no mean flow, there's negligible temperature gradients, so it simplifies the acoustic propagation. So we introduce this decomposition into our conservation equations, and then what we do is that every time we have a quantity that appears to be quadratic, like for example in here, we're going to have a rho prime v prime that will appear. Every quadratic quantity in the perturbation will be deemed small compared to the first order perturbations. Okay, so the idea is that rho prime, p prime, and v prime are small, and therefore their squared value is going to be even smaller. Okay, so that's what linearization fundamentally is. So at first order, we end up with a linearized equation for the conservation of mass and the linearized momentum equation. And a priori, those would be perfectly suitable to solve the acoustic field. But again, it's a little bit inconvenient because there are many unknowns. And the first thing we would like to do is to remove some of the unknowns, for example, the velocity component here. Okay, here we have three components of the acoustic velocity field. So it seems convenient to eliminate those variables. And this can be easily done by taking the time derivative of the first equation, subtract the divergence of the second equation, and because time derivative and gradient commute as operators, this eliminates already the three components that we have for the acoustic velocity perturbation, and we end up with this equation that starts to look like something familiar, like the wave propagation equation. Simply, it's not yet that operator because we have two variables here. Okay, we have rho prime and p prime, and we would like to choose one of those acoustic variables to describe the acoustic field. Okay, so then it's a matter of choice. The choice you might make is then to substitute, for example, p prime for rho prime by using what we call a constitutive equation for the perturbations. So a bit in the same way as you would have the perfect gas law relating pressure, density, and temperature. In here, we have a thermodynamic relation for the perturbations. Okay. Yeah?
Would it be possible to just lower the laptop a little?
Ah, yeah, sorry. My bad. Better like this?
Not surely, but this is fine. Thank you.
I can raise the screen, but that might be tough. Or yeah, I don't know if this can move. But
No, that's fine.
I think it, yeah, maybe changing chair might be easier than for me to move. Sorry, Manas, for this. Okay, so we have this thermodynamic relation. So it's a choice again. So you know, in thermodynamics, you have three variables to pick. Okay? Here we decide pressure, density, entropy. Could be enthalpy, could be anything else. But if once you make the choice of those three variables, it means that the perturbation of pressure might be due to the fact that the density has changed, and then you have the sensitivity of the pressure with respect to the density at constant entropy, or it might be due because the entropy has changed. Okay, and in an isentropic process, like we have during normal acoustic propagation, right? Because acoustic waves are small perturbations, and they introduce little non-adiabatic or non-isentropic processes. Okay? We can then assume that this S prime in here is going to be negligible for the propagation field. And therefore, we have this well-known relationship between pressure perturbation and density perturbation that are related by the speed of sound to the square. Now, the thing that we're going to do now, we are not going to do this approximation. We are going to retain the full equation because a priori, we don't know whether we will be looking at the source region or in the propagation region. And in the source region, you might very well have significant entropy perturbations, and that's actually what you are dealing with, right? When you play with combustion, you have massive amounts of entropy variations. Okay, so I'm going to retain this full property in here. The approximation you have there is the one that you can only make when you are far away from the source in the acoustic propagation. So I'm substituting, so what I'm doing in here, oops. So I take this expression in here and I decide to substitute for the density. So rho prime is going to be, what? Is going to be this, wait a second, yeah. P prime minus this guy in here divided by C0 squared. Okay, so that's the substitution we make, and then we end up with now something that is really a wave propagation operator, because we have selected one variable, and it is really an operator that applies to only one variable. And then everything automatically is projected on the right-hand side, and those are your equivalent sources of sound. Okay? So what you see is that you have different ways to produce sound in this linearized framework. This is what? This is fluctuating mass injection. Actually, what matters really is the volume injection, but that's up to 1 over rho 0, the same quantity. And that behaves as a particular kind of multipole. That's an acoustic. That's an acoustic. Monopole, dipole, quadrupole, octupole. Monopole, right? So that's an acoustic monopole. So you recognize this because there's no space derivative. The space derivative, as we will see later, is the one that is responsible for the acoustic efficiency on the one hand, so the dependence with the Mach number in the case of a flow. And the space derivative is also responsible for the directivity that that you have. But if you don't have any space derivative, it means that you have an omnidirectional source of sound, and that's going to be an acoustic monopole. So which prototype is the pulsating sphere, right? It's a sphere that remains in position and it is pulsating and pushing acoustic waves away in an omnidirectional. Then we have the second term that behaves like an acoustic. Second term, monopole, dipole, quadrupole. Yeah. Again. Adrien says That's a monopole. Remember the argument. There's no space derivative, right? No space derivative, monopole. So it means that entropy fluctuations behave the same way as a mass injection, as a fluctuating mass injection. And that's something from a combustion standpoint that you can feel almost with your hand. Because when you have unsteady heat transfer, which is one of the mechanisms by which entropy is increased, if you have unsteady heat transfer to a fluid particle, when the fluid particle is subject to heating, it's going to dilate, it's going to expand because of perfect gas law, if you want. So if you heat up a fluid particle, it's going to expand, and then it will gradually cool down by radiation, convection, conduction, what do I know? But it's going eventually to cool down, and therefore it's going to contract. And then you replace it by fresh fuel-air mixture. The flame front is passing again, it heats up and cools down. And you retrieve the idea of the pulsating sphere. Right? So you can almost feel with your hands that this term in here is going to behave, when it is related to combustion, of course, is going to be related to an acoustic monopole. Okay. Now, this guy in here is going to behave, so that's the non-uniform force field. That's going to behave like an acoustic dipole, because there is one space derivative, and this one is going to behave like an acoustic quadrupole because you have two space derivatives. Okay, so if you have a term that with a three space derivative, it will be an octupole. And then find the limit of my vocabulary. I don't know what four space derivative would give, but okay, that's a case that you will not meet very frequently in practice. Okay, so we have this multipolar decomposition of the equivalent source field, and this is in a linearized context. Okay, so the thing that you don't see here is turbulence. And the reason for this is that the first thing we have done is to linearize the equations of fluid mechanics. So if we want to recuperate turbulence, we must go one step back and not linearize. But then we'll see that we will apply fundamentally the same mathematical procedure of elimination of the velocity term. And then this will lead us to Lightfield's acoustic analogy. So Lightfield's analogy that somehow inspired from the procedure we have seen before. But this time we will take the full Navier-Stokes equations, keep them intact for as long as possible, and we are going to build up an analogy. And by analogy, we mean that if we consider the original problem, which is complicated, and which we have turbulence and fluctuating Reynolds stresses and all the things that are so complicated to simulate in here and to resolve in here, and you have a uniform propagation medium, this situation is analogous to the one where we have removed the turbulence, but we have put at its place something that radiates the same sound field at the listener point. Okay, so an acoustic analogy is really something to consider from a listener point of view. An analogy doesn't necessarily try to explain you what is happening there. And the thing that can be misleading with aeroacoustic analogies is that different physical interpretations of the source field can lead to the same acoustic field. And that's a general problem of the wave propagation equation, is that if you have your wave propagation operator and a right-hand side, there is an infinite number of ways to formulate a right-hand side that will give you the same measured acoustic field. There's the whole problem of inverse methods like acoustic beamforming and all those techniques that you try to guess what is the source field from a certain acoustic measurement. This is a problem that is fundamentally ill-posed because you have plenty of ways to distribute sources that will give you the same acoustic field. So again, remember that the purpose in here is not necessarily to explain to you what is happening there, but is to find a mathematical trick to wipe out the turbulence and put at its place something that you can calculate by CFD methods, for example, by a semi-empirical model, by a simple analytical argument. Okay, so that's the let's say the overall philosophy. Okay, that's clear on the philosophical aspects of the analogy. So, formally, how do we proceed? Well, we look at the two regions. We first look at the propagation region, and in the propagation region, there's no source by definition. That's how we define our propagation region, is when there is no source. Okay, so we know that this wave propagation operator applies there. We have zero because there is no source. And then in the fluid mechanics region, we have the fluid mechanics equations. Okay, so in the source region, we have the fluid mechanics equations. So the purpose of the game is to make this look like this, and automatically we'll have something there, right? That by recasting the equations of fluid mechanics into something like a wave propagation operator, I've effectively removed the complexity in here. I say that acoustic wave propagation equation apply everywhere, but then I will automatically have a right-hand side that will account for the effect of turbulence and all those mechanisms in the source region. Okay, so formally, it's exactly the same procedure than the one that we have seen before. We have our continuity equation, our momentum equation, and we take the time derivative of the first one, the divergence of the second one. The purpose is again to eliminate this term that we have in here, the rho vi, and then we end up with this. Okay, so that's a good start. We have the first building block, or the first brick, if you want, of our acoustic propagation operator. The only thing that would be very convenient would be to have a minus C0 square nabla square rho. Then it would really look like a wave propagation operator. But if it's missing, we just add it. That's relatively straightforward. So, okay, we just decide to arbitrarily subtract the term that we were missing. That, of course, has to be on the right-hand side as well. And now it really starts to smell like a wave propagator. The only thing that is not yet an acoustic propagation is that in here, it looks as if I'm propagating the density. But in an acoustic wave, it's not the density that is propagating, it's a density perturbation. Okay? An acoustic wave is not moving packets of fluids along. An acoustic wave is shaking fluid particles around the mean position. Okay? So it's a perturbation that we look for. So how can we introduce a perturbation? But same game as before, we just define a reference state that will be conveniently defined with respect to the propagation medium. So there we assume we have a mean density rho 0, a mean pressure P0, and a mean velocity equal to 0, because again, this is acoustic propagation in the medium at rest. And if this P0 and rho 0 are uniform and constant, they will automatically drop from the time and space derivative that you have. Okay? And that's how eventually you have shaped up your aeroacoustical analogy. So you have the left-hand side that is now the real wave propagation operator you were looking for, and everything that has been put on the right-hand side becomes de facto the equivalent sources for your new problem, where the medium is uniform and at rest. Okay, so this is the equivalent sources that are producing the acoustic field that you measure, and it contains a number of terms that looks like Reynolds stresses in here. Yeah, I'm sorry for those who are. Yeah, this is very low on the screen. You have something that will look like an entropy fluctuation term and viscous stresses. And so far, when you have done this, you have done zero approximation, right? So far, this is an exact reformulation of the equations of fluid mechanics. And as Miko used to say, still in his words, because it is exact, it is perfectly useless. Okay. So far, we have done nothing. We have just played around with equations. We have just reformulated Navier-Stokes. Navier-Stokes was convenient because we had at least 4 equations to solve our problem. We had continuity, which is scalar. We had momentum, which is vectorial. So we had 4 equations to solve our problem. Now we still have exactly the same number of unknowns, but we have only 1 equation. So that doesn't look like the smartest move so far. But the thing that is really smart with this analogy is that now we can play the engineers. And what I mean by play the engineer is that we can introduce orders of magnitudes, and we can try to estimate, grosso modo, the importance of the Reynolds stresses compared to the viscous stresses, and of the non-isentropic term in here compared to the 2 others. Okay, and that's by introducing those approximations that we will then facilitate our task by degrading the complexity of the source term. Okay, so typically, yeah. So just to finish this, so. I'm not going to go through the whole reasoning, but at large Reynolds numbers, we know typically that the Reynolds stresses are going to be dominant over the viscous stresses. Okay, that's what characterizes large Reynolds number flows. And for reasonably isentropic flow, like an isothermal jet or yeah, anything with any violent mixing, chemical reaction, or anything that would cause some significant entropy variations, this is going to be negligible as well. And then the remaining term will be the Reynolds stresses. Then we can then further approximate by assuming that at low Mach numbers, rho in here will be sensibly equal to rho 0. And then you have a rho 0 VIPJ, and that's something that can then be relatively easily calculated, well, relatively. And Sophie will elaborate a lot on how you can effectively calculate those Reynolds stresses. So I'm not going to discuss much further on the application of this. But one important point, maybe before we move further, is about the choice that we made here. So remember, we were here. Okay, so we took the time derivative of this continuity equation and the divergence of thing, and we ended up there. And then we decided, okay, we are missing a minus C0 square rho, nabla square rho. And then we decided to form a propagation operator for the density. That's fine, perfectly fine, but it's not the only choice that can be made. So we were there, and we decided to complement the left-hand side for density, and then we ended up with this equation. Right, so that's what the equation we ended up with. Now, a perfectly valid choice might have been different. Might have been to say, hey, look, in here I have something that is also a brick of our wave propagation operator. Okay, the nabla square p. What if I move this one to the left-hand side, added 1 over C0 square second time derivative of p prime, and then I bring then this one onto the right-hand side. So this is another acoustic analogy with an operator that looks different, but is formally the same in the wave propagation region, because remember, in the wave propagation region, we have the isentropic condition that is normally respected, and therefore, rho prime is effectively 1 over C0 square p prime, and C0 square rho prime is p prime. So the left-hand side is formally the same in the wave propagation region. But of course, this different choice leads to a different form of this term in here, the non-isentropic term. So the first one, corresponding to the Reynolds stresses and viscous terms, is the same. But the second one appears in a different form. Right? In here we have the source term corresponding to entropy fluctuations that appears as a kind of longitudinal quadrupole. And in here, it appears like a monopole. And both formulations are perfectly exact, right? So there's no mistake in here. Simply, numerically, it's quite likely that the second form will behave better for a combustion problem. Because for a combustion problem, you enforce the monopolar character that is more physical, if you want, of the non-isentropic term. If you rely on this form, it should, if you have an exact, but really exact numerical description of the source field, when you propagate to the far field, it should give you the same thing. But numerical errors will typically not behave the same way, because numerical errors will behave as quadrupoles, while in here numerical errors will behave as monopoles, and the solution should be monopolar. So it's this form, although a completely arbitrary choice over this one, will usually give you some better results simply due to numerical robustness aspects. Okay, so choices have to be made. Okay, and for a given class of problem, you might have a better choice for one or the other sort. For an isentropic noise generation, like a turbulent jet, this form and this form would be a priori just equivalent, because for an isentropic process, this term will anyway be negligible over this one, and then they turn out to be actually equivalent. Okay. Yep.
I'm probably saying something incorrect, but the two formulations are not related to the entropy wave generation.
Alors, the entropy wave generation would be comprised into. There, I'm a baby thermoacoustician, so you need to ask the specialist in here. But the entropy wave would probably correspond to this term in here, right? That's, I mean, it's what happens when you have an entropy spot that is advected through a contraction, right? So that's probably going to even though the entropy wave, isn't it dipolar in nature?
Yeah.
When you have a, I think it is, huh? So
there is, it depends very much. The first approximation when you go through a contraction is that you have a different force. So you have to accelerate fluid with different density.
Yeah.
And therefore, if you have the same pressure field, there is a kind of discrepancy between the acceleration of the hot fluid and the cold fluid. This induces a dipole.
Yeah, typically the light fluid will accelerate faster than the...
If you, the fluid goes through a contraction, the pressure change,
and you might have the
density change. And if the entropy fluid, which is a combustion product, has a different gamma Poisson ratio of the
CP
capacity at constant pressure divided by the heat capacity at constant volume, then it will contract a different way than the enabling fluid, and you have a monopole. So in general, you can have both.
In a general sense, you have both, and then depending on the difference of compressibility or not, you might have you might have the monopole or not.
Are convecting hot air in a cold air surrounding through a nozzle, you have only dipole. But if you are convecting an entropy wave of combustion product, have usually a much lower
the gamma of combustion product can be 1.1, 1.2, something like this.
Depending, but 1.2, 1.3 would be common.
Okay.
So there is a contrast in the gamma.
That's the full correct answer.
Okay.
Thanks, Peter. Okay, that clear this story about the. I know it's always the thing that is always a little bit puzzling with acoustic analogies. That different choices for the left hand side lead to different choices for the right hand side, and your sourcer doesn't do it the same way. We can continue to argue a lot about vortex sound theory. Vortex sound theory would make the turbulence appear as a dipole in first order, and then by massaging a little bit the source term, you make it appear as a quadrupole again. So just for you to accept that these analogies give you a certain form of the source field, and some are well suited to a given physical problem, and some are less suited to a certain physical problem. So for this, there's no other choice than to browse a little bit through the literature to see what are the practices, and eventually understand why people make a certain or another choice. Okay? Clear on this? We move on? Okay, so we have our wave propagation equation. So we have obtained this, with a Light-Field tensor. So I'm not going to rewrite Light-Field tensor every time. So I'm going to simply write the source term as a general source term Q of xt. So that's my source term. That you can have for either the acoustic density perturbation as acoustic variable or acoustic pressure perturbation. Now, when you have a differential equation of that kind, you know the mathematical procedure. You start usually by solving the homogeneous form. Okay? And the homogeneous form is by putting the right-hand side to 0. And when you solve this differential equation with a proper set of initial and boundary conditions, okay, the boundary conditions will give you the general shape of the solution. Okay? Is it going to be like a sine wave? Is it going to be a Bessel function? It's really the boundary conditions that decide of the shape of the solution. And you usually end up with a solution that is defined up to a certain constant, okay, or to a certain more precise shape, okay. And this you obtain it by introducing the shape back into the left-hand side, and now by recuperating the right-hand side. So the thing we are going to do now is we are going to look at the general solution of the homogeneous solution for different configurations. Just a quick word on what we are going to do for the duct acoustics part. In particular, we are going to look at the problem in the frequency domain, because it's more convenient to work in the Fourier domain, because we will see that it gives you immediately an interpretation of the results in forms of propagating waves, evanescent waves, that is more practically usable. Okay, so how do you go from the time to the frequency domain? But we presume this convention it's just a convention. Huh? So any quantity will be given a harmonic behavior with plus I omega t. This another convention could be minus omega t, in which case the result will be the complex conjugate of the result we have here. Okay? And then when you introduce this decomposition, you will end up with an omega square over C0 square, and omega over C0, so the pulsation, 2 pi f divided by C0 is what we call a wave number, K. Okay, so the wave number K will have dimensions meter minus 1. Okay. So what are general solutions? The first one that is the most known and the most useful, and the one we will use in curves analogy in particular, is the Green's function. So the Green's function is the solution of our initial wave propagation problem with a very specific kind of source field, a very specific kind of right-hand side. It's something that looks like a gunshot. What do I mean by a gunshot? Is something that is point-wise in space and point-wise in time. A short word about notations here. In many aeroacoustic books, you will find that y, which is a vector here, it's boldface, so it's y1, y2, y3, is the coordinate of the source. And you will find that x is the coordinate of the listener. Okay. In the same way, t will be the time at which you listen to the sound, and tau is the time at which it was emitted. Okay, so we talk about emission times tau and listener time t. And then you have this wave equation, and in case of free field, the only boundary conditions that apply are that the acoustic field should decay at infinity. Okay, you can formulate it. Adrien will maybe mention this as a Sommerfeld boundary condition. I don't know if you speak about acoustic propagation and the treatment of non-reflective boundary conditions in a finite element context, but this, in that case, it would be the Sommerfeld boundary condition that simply states that the acoustic field has to decay at infinity. And so, if you are in free field, the good news is that we know the solution. It's given to you, and the solution is this function g that I call 0. The 0 is for to indicate that it's a free field boundary condition. It's this delta function, okay, which is the Dirac function that we have in here, is the same. And we have a behavior in here that as a denominator, which is like 1 over r. So this is sensible because it mimics the effect that spherical waves are decaying as the inverse of the distance from the source to listener. Okay, so that's physically consistent with this. That's the decay you need to have conservation of acoustic energy when you go at different distances. Now, the thing that is really nice about this numerator in here is that it defines automatically what we call a retarded time. Well, first thing, do you know what is the property of the delta function? So what is the definition of the Dirac function? The definition of the Dirac function. Do I have some things to write on this? So the definition of the Dirac function will be that the integral in 1D from minus infinity to plus infinity over certain f of x, say delta x minus psi, dx is equal to f of now f of psi. Okay, so that's what we call the sampling property of the delta function. So if you have a function f that looks like this, and if you have your delta of x minus psi, is going to be non-zero only where x is equal to psi. So it means that your function delta will look like this. So it's 0 everywhere. A kind of what I call, because I'm not a mathematician, so something that I call a funny infinite value. So it's a funny infinite.
If you move it in front of the screen, then you have light.
It's magic. Right, so you have your function f of x, which is this one. You have your function delta of x minus psi, which is this one. And it's 0 everywhere, your function, except where its argument is equal to 0, where it takes a value of a funny infinite because it remains an integrable infinite. Okay, so effectively, this integral is equal to 1. But this integral is equal to the value taken by the function f of x at this argument. Okay, so that's a property that we use a lot when we try to look for integral solutions of our wave propagation equation. So it's very convenient. You have something complicated, you integrate it with a delta function, and it samples the rest of the integrand at this 0 of the argument of the delta function. All right? So it means that this implicitly, this expression in here, will become interesting only where the argument of the delta function is equal to 0. And that defines what we call a retarded time. So tau star is the solution of the so-called retarded time equation that gives you the time at which you must know your source if you are interested into the acoustic field at a certain position x and at a certain time t. Okay, so it means that if I'm interested in knowing the noise now, I must know what he has said a couple of milliseconds before. Okay, because we have the time of propagation. And the time of propagation is, of course, the distance divided by the speed of sound. Okay, so it's trivial. Now, there are a couple of useful properties of this Dirac function. Well, we mentioned already it's convenient to obtain an integral solution. And then you have another useful property, which is the property of reciprocity. So sometimes you have some instances where it's a little bit difficult to calculate the problem or to solve the problem when the source is in here and the listener is in there. But it turns out to be easier to solve this problem, where the source has been moved here and the listener is here, right? And if you can solve this, but then you can swap back, if you want, the coordinates, the time and spatial coordinates for the source and for the listener. Okay, so the method of compact Green's functions of Michael Ho proceeds this way by using this reciprocity. Okay, so now how convenient and how useful is it to have this Green's function? But it will allow us to obtain an integral solution for our problem. So how so? I've written in here the initial problem we have. Okay, so that's the initial problem we have. You know your source field, you know the distribution of monopole, dipole, quadrupole because you had a good CFD solution. You had the best large eddy simulation that gives you the Reynolds stresses, the non-isentropic terms, and everything. Okay, so the right-hand side is considered as given to you, and the question is, okay, nice. What is my acoustic field now? Anywhere in the propagation medium. And it's good to have this solution because then you can combine the solution for your Green's function and your initial problem. So how do you proceed? You take the first equation, you multiply it by the Green's function, and you integrate it over a certain control volume V, okay, that contains the sources, that contains the listener, obviously, and that might contain also what we will consider to be hard reflecting surfaces. Okay, so we define our control volume, and so we take this one, we multiply by G, integrate over a certain amount of time from an arbitrary time t0 to a certain time t, and then over this volume. And then we take the second equation, we multiply it by our unknown rho prime, and then we do the same procedure. We integrate this equation then over the same control volume over the same time interval, and I skipped some steps in here of the derivation, but you end up with this solution. You end up with this integral solution. Okay, if you're interested into the details, I'm happy to provide the details of the derivation. It just takes one slide, but it's not the most interesting thing. Now, the thing that matters in here is to realize that the boundary of the control volume in a general context is made of two surfaces. You have one surface that is surrounding your whole system, and that you might decide to bring to infinity. Okay, it's completely arbitrary how you define a control volume. But then you have another surface that must exclude the solid body, right? Why do you need to exclude the solid body? Because remember, this is all obtained from Navier-Stokes equations, right? You would not apply Navier-Stokes equations inside of the table, right? You would apply solid mechanics equations. Okay, so if you want your equations to be valid, you need to exclude the region of the domain where they are not valid. Okay, so that's how you end up with this boundary in here. You have a boundary in here, and you have a boundary in here. And the normal is pointing outward, so it means that the normal is pointing in this direction in here, and it's pointing inside of the solid body in this region. Okay, what do we have here? We have a first term in here that consists in effectively sampling our source field in the sense of multiplying it by a Green's function. And remember, the Green's function contains this delta function. Okay, so we will effectively sample our source field at particular position and particular times. Okay, so we will look at the source term at a certain time corresponding to the distance from the listener. So that's the first equation here. And then we have a second equation here, which is a byproduct of some integration by parts that we did along the way. That contains a number of terms that we would like also to simplify as much as possible. So how can we simplify this? Well, there's a first thing that we can realize is that the term you have in here is effectively corresponding to vibrations of your solid body. If I'm considering the boundary that is in here. Why am I saying that it corresponds to vibration of the solid body? It's because C0 square rho prime is P prime, and the gradient of P prime projected onto the normal by the linearized momentum equation is the normal velocity. Okay, so if you just go back to the linearized momentum equation, you will see this. So this term is effectively representing the noise that is radiated through the vibrations of the surface. Okay, so if your loudspeaker membrane is producing sound, it's because it is vibrating. Okay, so that's the problem, and that's generally considered as a vibroacoustic problem. Okay, because you prescribe, you know the boundary condition of your domain, you know how fast your surface is vibrating. So this is for you a source term, a boundary located on the boundary for the acoustic. So it's usually something that is easy to solve in the sense that you have first determined the vibrations and then it becomes an input. Now, if you are looking at reflection by this table, I can presume a priori that my voice is not loud enough to make the table vibrate very strongly. So then you have the other problem, which is a problem of reflection. Okay, and the reflection is simply the fact that you have a certain acoustic velocity, and when it reaches the table, it must go to zero. So there's a non-penetration boundary condition, and so there is a kind of minute reaction force that is exerted by the table to bounce the wave back. Okay, so and this corresponds to this term. This is effectively the acoustic reflection. So in other words, the sound field that is collected by your listener, it's this component in here, which is a directly radiated sound field from the sources, and then you have another source term in here that corresponds to the sound that was going towards the solid body and reflected back to the listener. Okay. Now, I said that if the table is not vibrating, this one goes to zero. The problem that you have is this one. So how do you effectively treat this one? There's one way to solve the problem. It consists in finding a particular kind of Green's function that satisfies a particular boundary condition. Because the thing when I introduced this Green's function in here, I didn't mention anything about the boundary conditions, right? I didn't say whether this was a free field Green's function, a ducted Green's function, an infinite half plane Green's function. So there must be one Green's function that satisfies this equation plus a set of boundary conditions that might be conveniently dGdn, or the gradient dGdyi projected onto the normal to the surface, equal to zero. And if dGdn is equal to zero, then it eases our life a lot, because then we don't need to know the unknown field on the reflected surface anymore, right? So we have the contribution in here becomes automatically zero. Okay? Otherwise, if you don't have this, it means that you must know, in order to know your solution in here, you must first know your solution in here. Okay? And that's what boundary element methods work with. I mean, you first start by solving the so-called potentials on the surface, and once you know the potential on the surface, then you can propagate them to the far field. Okay, but in here, if you are lucky enough to have what we call a tailored Green's function, then this problem is simply resolved by this property. Okay, so this can further simplify into this, so where simply the second integral has disappeared. In two instances, either you have no solid surface in the propagation region, and then it's comfortable because this surface doesn't appear, you only have this surface, and this one you can bring it to infinity, and if you bring it to infinity, all the contributions in here decay. Okay, that's something you can prove. The Green's function decays as 1 over r, okay, as 1 over the distance, so the gradient is 1 over r squared. And even when you, and rho prime, it will be 1 over r, so this is 1 over r cubed. And even if you go to infinity, this goes as r squared. Okay, so the net result is something that decays as 1 over the distance. So if you bring this control surface to infinity, all the terms that you have in here decay to 0 automatically. Okay, so that's the easy case. So if you don't have any solid surface in the propagation region, then easy peasy, this one goes to 0. If you have a solid surface that you need to exclude by this control surface in here, if it turns out to be non-vibrating, and if you are lucky or smart or both enough to have a tailored Green's function, then you effectively have this property, and then you end up with only this solution. And in the case, G becomes a tailored Green's function. Okay? Right? So, which shows all the interest of having a tailored Green's function, because it simplifies a lot. And the thing that you end up with is an integral solution. And something that is a key to remember, that integrating is generally a very healthy activity. What do I mean by this is that your source term, you will see in practical cases, the source term Q that you will get from your favorite LES or DES or I don't know, whichever numerical model, or even worse, experimental data, is usually contaminated by some noise. If you take something that is noisy, and if you integrate it, the relative contribution of noise decreases a lot. If you define noise as what it is in a statistical sense, something with 0 mean value, right? Then if you integrate something with 0 mean value, you end up with 0, right? So it means that having an integral solution is usually a very good idea because you can afford to have a mildly wrong source field. And by mildly wrong, I mean, you need to place the cursor carefully, of course, but a mildly wrong source field, let's say contaminated by some random-ish noise, and if you use an integral solution, your acoustic field might still be quite okay. Okay, so that's the, I mean, for the main advantage of this integral solution. Now, one aspect of the problem that we mentioned is, okay, this all assumes that we have a tailored Green's function. Now, what tells you that obtaining a tailored Green's function is easy? Well, actually, the problem with tailored Green's function is that they are generally as complicated to obtain as your initial acoustic field, because you solve the same problem simply with a different source term. But there are nevertheless some cases where the geometry is simplified enough and where you can derive once for all your tailored Green's function, and then you can reuse it. So you have some libraries, if you want, of tailored Green's functions corresponding to different geometries. So in some cases, the geometry is really simple, and you can have a fully analytical Green's function. If your reflecting surface is an infinite plane, it's really easy, because then the solution is the same as if you put an image source on the other side of the image plane. And the contribution of the direct field and of the field that is reflected by your plane is the same as the direct field plus the field of the image source, because the acoustical path in here, so imagine my plane is in here, right? The acoustical path that is in here is the same as the acoustical path that is in here. Okay, so for this reason, it's really easy. If you have a semi-infinite plane, it's a little bit less easy, but there's still an analytical solution derived by Fock, Williams, and Hall, and it applies in particular to a trailing edge noise. So if you have an airfoil and you have turbulence passing in the vicinity of the trailing edge of the airfoil, but locally, so just here. So if you have an airfoil, and if you have some turbulence that develops over the airfoil and is passing in the vicinity of the trailing edge, your Reynolds stresses in here, the rho 0, sorry, Vi, Vj, that you need to scatter by the geometry, but you can scatter them by an idealized geometry that is something like this, right? It's something that is infinitely sharp, that has an end here, okay, and that goes to infinity. And for high enough frequencies, the chord in here is going to be large compared to the acoustical wavelengths, and if the chord is large compared to the acoustical wavelengths, this infinite flat plate is a fair approximation of the geometry of your chord. If you reduce the frequency, it starts to be a little bit more complicated, but you can nevertheless proceed by this approach. Okay, so that's where one instance where this Green's function is useful. If you have infinite straight ducts, like something that is rectangular but keeping its shape and dimension along the axis of propagation, so rectangular, cylindrical, annular, we will see this, then you also have analytical Green's functions. In other case, the geometry might be a little bit more complicated, but still easy enough to allow some what we call semi-analytical Green's functions. They are obtained by an analytical development where at some point you need to make some approximations. Okay, and then it means that the Green's function is valid in a certain limit. For example, the compact low frequency, so the compact Green's functions by Rho are valid at low frequencies because there is an assumption of acoustic compactness. Yeah, by the way, acoustic compactness, familiar concept? Definition is?
Like when your length scale are way smaller than the acoustic.
The acoustical wavelength. Okay, so if your scattering body is small compared to the acoustical wavelength, then you can effectively make this compact assumption, and then you have this thing here. But again, there is an assumption. Then there are some methods that are not good for health. Wienerhopf is a sport by itself, so I encourage you to play with it. I tried, I didn't manage, and at my age I think it's too late. But the Wienerhopf technique is one of those analytical techniques that allow you to calculate, in particular, the problem of scattering by discontinuities. The case of the semi-infinite plane can be treated in a Wienerhopf context. When you have sound radiation from the outlet of a pipe, it's also something that has a marked discontinuity between one propagation region and the other one, and you can use a Wienerhopf technique for this also, so I refer you to the literature for this. The Schwarzschild technique is a little bit easier. That's something that was used a lot for, by the case of airfoil noise, for what we call the problem of trailing edge, leading edge backscattering. So I told you that this problem of trailing edge radiation can be easily calculated by using this semi-infinite plate approach. Now, the acoustic waves that are going to be radiated by your trailing edge, eventually they will meet the leading edge. And the leading edge, even though it's a milder singularity than the trailing edge, it's less sharp. If the acoustical wavelength is large compared to this radius of curvature, it will still look like a singularity. And then you have a backscattering problem, that is the one of the acoustic wave reaching the leading edge and being backscattered to the field. And then it's a semi-analytical approach because each step is an analytical solution, but each step is the predecessor solution for the next iteration. Okay, so at some point when you add the number of trailing edge backscattering, leading edge backscattering, because this acoustic field is going to go back to the trailing edge, of course. So you have another secondary scattering that takes place. At some point it converges. Okay, so normally except it has very specific frequencies, the series converges, and then you can have an analytical solution for this technique. And the Schwarzschild technique is because each solution is the solution of the Schwarzschild theorem, which is a theorem that was established for electromagnetics initially, but works very well also for acoustics. Okay. Another instance of semi-analytical Green's function is, let's say that your duct is not completely straight, like slowly converging or slowly diverging, as is the case, for example, for the nacelle of an aero engine. Okay, if you look at the nacelle of an aero engine, you have the fan, and then you have the duct that is slowly converging, and then you can actually generalize the solution that was obtained for this by introducing the fact that the duct is slowly converging or diverging. And then you have some analytical developments by Schurt and Schram in Eindhoven that have been very much applied for this problem of aero engine nacelle propagation. And then you have all the other cases for which you need to make the people working here rich. Is the case where you need to buy a license because the geometry is really too complicated. There's no analytical, there's no semi-analytical solution. And then there's the only alternative becomes in discretizing your wave propagation operator and seeking a numerical solution for your Green's function, okay, or for your acoustic problem. And then you have Adrien who's going to save the world with you this afternoon, right? So he's going to talk about finite element methods, boundary element methods. I'm not sure, probably not because it's out of fashion nowadays. And then so those are called usually low frequency techniques that Adrien will explain. You have high frequency techniques like ray tracing methods, statistical energy analysis, and then you have the whole gap in the middle to try to bridge the, let's say, for the whole frequency range. We have multi-grid techniques, fast multipole them, and okay, this is completely outdated. Probably this is an area of very active development, but in here in particular, to develop numerical solutions for the Green's function. Okay. So that was a long discussion about Green's functions, hopefully for good reasons. So now let's look at a particular solution. So I told you about Taylor Green's functions for ducted geometries or ducts. So we have a general solution that, a general configuration that is this one. So X and Y are the transverse directions. Z is the direction in which the cross-section is not varying. And we work in the Fourier domain, so meaning we have this decomposition for the pressure, for the velocity. This leads us to the homogeneous Helmholtz equation with the wave number. And the boundary condition that you have in your problem, there's no boundary condition a priori on this direction. And the case we are going to treat is actually the case where the duct is infinite. Okay. And if the duct is infinite, it means that it takes a really long time for a reflection to come back, but really long. Okay? So the boundary condition is only outgoing waves and no reflected waves, if you want, or anechoic boundary conditions. And the boundary conditions that you have along the wall is, of course, a Neumann boundary condition, so it's a non-penetration boundary condition. And this is the expression. This is equivalent to this boundary condition using the linearized momentum equation that we have seen before. Okay. Now let's make the problem a little bit more specific. We have a rectangular duct. If we have a rectangular duct, it seems like a good idea to work in a Cartesian framework. So the Nabla square operator is going to split up as this, and because of this form of this shape of the operator here, what we are going to try is a mathematical method that is called the method of separation of variables. Okay, so it proceeds this way. You postulate that your solution might look like this. Okay, that the solution for so P in here is the Fourier component. So we work in the Fourier domain. We postulate that it's the product of three functions, each of which depending on only one variable. Okay, so we have something you kind of decouple, let's say, the solution in the three directions. And if you substitute this into the Helmholtz equation by the method of separation of variables, you end up with the result that your partial differential equation, your single partial differential equation, can be split into three ordinary differential equations. Okay, depending each of them on only one component. And those three equations can be written like this, like that, and like this. Okay, so basically, you first postulate a solution so you first separate in the direction x, then in the direction y, and you introduce some general constants alpha and beta here. And then, as a result, the third equation has to look like this because you want the sum of all those terms to be equal to what you need for the Helmholtz equation. Okay, and you know some solutions for this. Once you introduce the Neumann boundary condition that the acoustic field, the acoustic velocity field must have a normal component equal to 0 along each of the faces of the duct, we end up with a solution for f that is cos alpha n x, where n is an integer, 0, 1, 2, and so forth. Alpha n is n pi divided by a, where a is the dimension of the duct in the direction x. Similarly, you have this solution for G, and then for H, you have a more general solution, which is going to be an exponential of A, K, and M, where K are the modal wave numbers that are given by this. So basically, what you choose in here, you choose a value of n. Okay, any integer value will do the job. Any integer value of m will do the job, will satisfy the boundary conditions. And once you have done this, you have a certain value of k and m that comes automatically because you fix the frequency. Okay. And then your general solution will be a superposition of each of these modes. Okay. So we call those modes, okay, because they are eigen functions, if you want, of the acoustic problem. So the general solution is going to be a sum from n to 0 to infinity, m from 0 to infinity, of cos alpha n x, cos beta m y, and these waves that can be conveniently separated into what we call right-going wave and left-going wave. Okay, the solution with a minus sign will be a wave going to the positive x direction, and the one with the plus sign will be going into the negative x direction. And any solution will be a superposition of both. Okay, and as I mentioned, this is the general solution of the homogeneous problem. Okay, so it's not the solution of your problem. It's the shape that your solution can potentially take. Now, the shape it will effectively take will depend on the source. Okay, if you have a source that excites only plane waves, you will have only plane waves. If you have a source that excites only transverse modes, you will have only transverse modes. Okay, if you have a general source, the solution will be a superposition of those modes. Okay, but it just fixes the general allure, I would say, the general shape of the solution. Right. Now, maybe an important word now about this K and M, because so far it's a sum that goes from 0 to infinity. Now, in practice, you don't need to go to infinity. The reason is that some of the modes will not propagate. So how can they not propagate? It depends on the sign taken by K and M. Remember, K and M, that's this square root in here of K squared, so that's depending on frequency, that's going to be something real. And alpha n and beta m, which are your eigenvalues that you have adjusted by letting n and m vary. Okay. So, what is under the square root in here can be positive or negative. If it is positive, everything is fine. You have exponential minus plus something I, something positive, and z. So that's effectively something that is going to be superposition of cosines and sines. It's something that is a propagating wave. Okay, everything is fine. Now let's imagine that the thing you have in under the square root now becomes negative. Negative becomes square root of something negative will be I times the square root of the positive. So we'll have I times I, it's going to be minus 1. And then you have minus 1 that will be either multiplied by a minus or by a plus. If it's minus 1 multiplied by the plus, it's something that is exponential minus real z. That's what we call an evanescent wave. It's a wave that is exponentially decaying. Okay? If you take the minus times minus 1, it means exponential something real times that. And now this is something that is exponentially growing, but this is non-physical. Right? I mean, where would this energy come from? I mean, there's nothing in nature, as far as I know, that can grow exponentially. Okay, so that's a solution that you simply discard out of physical ground. Okay, so you see that depending on the sign of what is in there, you are going to have either propagating waves or evanescent or exponentially decaying waves, and that's what defines the limits of your problem. So at low frequencies. So let's say that you fix a certain mode. You fix n equal 3, m equal 4, right? So the third transverse mode in one direction and fourth in the other direction. If your frequency is too small, this will be negative, and you have an evanescent mode. If for the same pair of values n and m, your frequency now becomes large enough, now this will be positive, and now you have a propagating. Okay, so it means that for a certain mode to be propagative, you need to reach a minimum frequency, and this frequency is given by the eigenvalues alpha n and beta n. Okay, so you can very easily determine, because these are purely given by the geometry. If you know the dimensions of your duct, you can very easily predict which mode is going to be propagative or not. One particular mode is the case n equals 0, m equals 0, but alpha n is equal 0, beta m is equal 0. And square root of k square, remember k is the wave number, it's always real, it's omega divided by c0. So it means that this one will always be equal to k, and therefore the plane wave mode is always propagative. There's no way, as far as I know, to cut off a plane wave mode. Okay, it will always propagate. Is the other modes that have these thresholds of frequencies to become propagated. Right? The clear the story about propagating evanescent modes? Now, if it's clear for the rectangular duct, it's just exactly the same game for cylindrical duct. Simply, the eigenfunctions will look a little bit differently simply because your operator in here will look differently. So now your nabla square operator in the Helmholtz equation is expressed like this in cylindrical coordinates. And your method of separation of variables gives you this set of ODEs to solve. And the solution now will be a superposition of modes that are azimuthal modes, where the only boundary condition you have is the boundary condition of periodicity. So if you go around your duct, you must retrieve the same value every multiple of 2 pi. Okay, so that gives you this shape with m being integer value, but positive or negative. You have then the radial function that is now a Bessel function of first kind, where m is the order of the Bessel function, and mu is going to be the mu 0 of the derivative of the Bessel function, but this is all tabulated for you. Okay, so that's what we have in here. And then likewise, just as before, we have a dependence along the propagation axis that is the same as before, simply with a different value for k and mu. But same game as before. You are going to have waves that are going to be propagating, evanescent, and that depends on whether your frequency is large enough compared to the alpha and mu value that you have. Okay, so same story. Now, if you want the general solution, it's a superposition of all the azimuthal modes from -infinity to 1, all the radial modes from 1 to infinity. You have just this form in here for the radial dependence, where you have this normalization factor that is introduced to preserve the energy for each mode. And then same story, huh? You are going to the same story. The planar mode is going to be always propagative. There's maybe just one mode that is, or one eigenvalue that is convenient to remember, is the one that corresponds to the first azimuthal mode passing. So if you look at the mode shapes, so this is the plane. So this is a solution using the Siemens tools. This was using Virtual Lab, but I think the SimCenter gives pretty much the same results. This is the plane wave mode that you have. Now, if you have a boundary condition that corresponds to the first azimuthal mode, but you see this azimuthal mode that is spinning in one direction because it's the +1, it would be the -1, it would spin in the other direction. And then you have the mode 2, 0, and then the next passing mode is the first radial mode, which is kind of pulsating along the duct. Okay, a mode that is kind of reflected over itself and then on the walls and on itself on the wall as it propagates. Then you have the mode 3, 0. And the thing that you see is that if you solve this problem numerically with a frequency that is high enough, the mode propagates. Now, if you impose the mode shape, but if you tune down the frequency, what you see here is this exponential decay. Okay, so the numerical solution gives you the evanescent modes, of course, as well, because the numerical model doesn't know about the geometry of your problem, right? So that's the exponential decay that you see in here. It is pretty fast. So I told you that there is one eigenvalue that is worth remembering, is the one for this one, because this one is the first pattern mode. If you increase the frequency, the first transverse mode that will appear is this one. And it's very often convenient to know whether you have only plane wave propagation in a pipe or if you have to bother about the higher order modes as well. Because it depends on how many microphones you need to put along your duct. If you have only plane wave mode, your microphone can be here and here, or here, or here, or here, or here. it's not going to make any difference. If you have azimuthal modes, then you need to discretize them in the azimuth. Then it starts to be a little bit more troublesome. So the first eigenvalue that you have is for Kr, where R is the radius of the duct, 1.84. And if you work out the expression to find the frequency, you will find that it's pretty close to 100 meters per second divided by the radius. Okay, so if you want to know if a certain mode will be exciting higher order modes or only the plane wave mode, you take 100, you divide by the radius of the duct, and you will have a pretty quick estimation and pretty accurate estimation of the frequency. So if your frequency is below this, no worries, only plane waves. If it's above it, then you need to think about what it means for your car.
In air.
Yes, in air. Yes. No bubbly flow, no thermal effects, nothing. Yes, Karman.
So yes, I don't want to take too much time, but I have a question on the numbering of the modes. The rectangular one was like KMN, it was MN starts from 0 and 0, but here news starting from 1.
Yeah, depending on the reference, you find different notations. In here, I try to be consistent with notation. Sometimes you see the mode plus minus 1, 0, but the point that mu in here is the first non-trivial zero of the derivative, and there is nothing like a 0th first root of the derivative of the Bessel function. Normally, you will start from the first non-trivial root of the Bessel function. So in some references, you will find the numbering for the radial mode starting at 1, which means no radial dependence. That's the thing that is a bit confusing. 1 means no radial dependence, and in some other literature, you will find 0 labeled as 0 because then it's more logically compared with the. It's a matter of convention. It depends on how you decide to number or to index the non-trivial zeros of the derivative of the Bessel function.
Is there any particular reason why we use Bessel functions in circular graphs and not in rectangular?
Yeah, but that's by virtue of this operator. I mean, the shape of the Navier operator gives a radial derivative that looks like this, and this is a Bessel equation.
Oh.
And the solution of the Bessel equation is Bessel functions. Typically, every time, you have to be careful, but many times when you have something with a circular symmetry, being the vibration of the drum, of the skin of a drum, or anything with a circular symmetry, you will often find a Bessel function as a solution. That's because your differential problem writes as a Bessel equation. Right? Any other question? Yep.
About the evanescence of the modes for the cutoff frequency. So you're saying that in those scenarios you neglect those modes, right?
Yeah. With some bemols, but yeah.
But if you have the particular solution, so you have kind of a response at that frequency, it's higher than the decay,
Yeah.
not continually excited.
The problem is that the rate of decay depends on how far you are from the cutoff frequency. If you are just below the cutoff frequency, your mode will be exponentially decaying, but with a very small negative exponent. So you can have an evanescent wave that still propagates, so to speak, over a certain distance before it decreases. So you have to be cautious when you are playing around. I mean, if you're really close to the cutoff frequencies. Yes, you go from a propagating mode to an evanescent mode, but locally it can be slowly decaying. So another thing that becomes really puzzling is when you have a mode that is decaying and then you re-enlarge the duct and then it becomes propagative. Because an evanescent mode, in theory, by the equations, doesn't carry any acoustic energy. If you calculate the acoustic intensity associated with the cutoff mode, the energy is 0. But still, if you re-increase your duct, then it becomes passing again. And then there is a conversion between non-propagating to propagating modes of a mode thing that was not containing energy initially. So then the discussion starts to be a little bit more tricky. Okay. Well, I need to speed up a little bit. So Kerr's analogy. So if you followed what we did so far, we have seen actually integral analogy already, because it's just an integral solution of Light-Hills analogy. Simply, there's something that I did previously is to assume that I had a tailored Green function at my disposal. So that's exactly the same solution we had before. Simply, instead of Q, I've reminded that this was actually the double divergence of Light-Hills tensor. Okay, so that's exactly the solution we have seen before. And so far, I've only considered the case where I have either a tailored Green function or no solid surface. Now, what happens if you have solid surfaces that are not Taylorizable? Okay, so you have something that has a geometry like a cylinder within a duct. It's already complicated enough to be non-Taylorizable. I mean, I don't know of any tailored Green function directly applicable for this. So then it means that having no best clue about a Green function than the free field one, but you use the free field one, right? I mean, you would like to be smarter. You would like to have a tailored Green function, but you don't have one. But you need to pick one, and at least the free field Green function is well known. You have this delta function that is convenient, and then that's what you do. So you use G0, and then you solve this problem. And how do you solve this problem? But the first thing that you may wish to do is actually to apply some integration by parts to this term. Why do you want to integrate by part this term? It's because I told you that integrating is good for health. Accordingly, differentiating is very bad for health. Okay. Remember the term Tij in here. That's Rosio VIVJ in the best approximation. That's something that you get from an LES or experimental data. It's something that is generally not infinitely accurate. Okay. Now derive something that is contaminated by noise, and you go for failure typically, because this emphasizes the contribution of noise compared to your signal. So to derive something you don't know is generally a bad idea. But if you apply some integration by parts, then you transfer the derivative to the Green's function. And if the Green's function is the tailored one, you know it analytically. You can derive it 27 times if you like. It's a particular form of perversion, but you can derive it plenty of times, and it will remain exact. Okay. So let's do this. We integrate this guy 2 times by parts. And then we end up with this. So job accomplished. The 2 space derivatives are transferred to the Green function. This is a much healthier formulation already. But then, of course, you have the byproducts of the integration by parts. Okay, so integral of u dv is uv minus integral of v du. Okay, and this is the integral of v du that appears in here. And then what happens is that you have some kind of black magic operating, because the terms that are underlined, they come to cancel exactly the terms that you had in your integral here. So you have a c minus c0 squared d rho prime dy ig, which is this one. And then you have the term in here that comes to cancel exactly this one. So, okay, that's good news when terms cancel each other. It's usually good for the solution. And then you introduce the fact that your surfaces are non-vibrating. Okay, so that's a flow inside a certain domain, but nothing is vibrating over there. And then you introduce the choice that you have made for the free field Green function, and you end up with this solution. And this solution is exactly the one that you had for Light-Hills analogy, with one additional guy in here. So Sophie will speak more about Light-Hills analogy. So this would be a quadrupole. So Sophie will come back to this more in depth. And this will appear as an acoustic dipole. Okay, so it means that your initial problem that you have in here can be reformulated at a sum of different kind of sources. You have quadrupoles that correspond to the turbulence, say, in the wake or in the boundary layers. Okay, and you are going to have also dipolar contribution corresponding to the pressure fluctuations on the surfaces. And this is the integral solution according to Karman. Okay, so it's nothing. Because energy holds in one side, and if you have followed the derivation that we had before with the Green function, you have exactly the same. Now, the thing that is just mildly disturbing in here is the fact that when you start with this solution in here, okay, you have some source field that corresponds, in the case, to volume integral. So you have something that looks like the Reynolds stresses that you have to integrate, and then you have a scattering integral. So it means that these sources have to be reflected by the boundaries in order to leave the domain. So you have your Reynolds stress that is, and the sound is reflected by the cylinder, reflected by the duct, and eventually leaving the domain to radiate to the small guy in here, okay, in the circle. Now, when I'm doing all these derivations, what is happening is that I end up with a system where there's no scattering integral anymore because it was cancelled, and we just have equivalent sources. So it means that each of these sources is shooting straight through the solid surfaces, right? The quadrupoles in here are radiating directly towards the solid surface. The quadrupole in here, the dipole in here is shooting through the cylinder, doesn't see the wall, radiating a straight line. Because I'm using a free field Green's function, and free field Green's function doesn't know about reflections. Okay, so what was the trick? It looks highly non-physical as a solution. But it's nevertheless very physical if you think that your P prime in here, by the definition we've applied before, it's any deviation from P0. It's any deviation from the pressure in the propagation region. And being any deviation, it means that it's going to account for the hydrodynamic pressure fluctuations due to the nearby vortices, but also to the acoustic field. So the acoustic reflections are comprised in here. Okay? They are not explicitly apparent in the form of a scattering integral in here, but the acoustic reflections are already comprised in here as long as your solution is accurate enough. If you have a solution for P prime that you get from a compressible large eddy simulation, high order, and let's say in the immediate neighborhood of the source field, where it's reasonably well calculated, then you are in safe hands. Okay? Then the acoustic reflection and the scattering effect of the surfaces is comprised in your source term. The danger comes if you use an incompressible model to get your source field. And the problem that the temptation is usually very large to use an incompressible model because the realm of aeroacoustic analogies is low Mach number flows. So a low Mach number flows, usually you don't like to pay for the cost of solving a very stiff system. Usually you are happy to solve only the incompressible solution. But in that case, your P prime in here is going to accommodate only the hydrodynamic pressure fluctuations, the incompressible pressure fluctuations. And there you have to pay attention. Okay, so there are some circumstances where it works very fine. And typical example is whenever you have a compact source region. If you have a compact source region like a cylinder in cross flow, so you take a cylinder of 10 centimeters, 30 meters per second. If you work out the Strual number and the Helmholtz number, you will see that your thing is extremely compact. Okay, because the dominant acoustical wavelength will be of the order of 6 meters, and you have a 10 centimeters. And so the cylinder is very compact. And in that case, it's okay because a compact body is acoustically transparent, right? If I put this in front of me, you hear me just fine, right? Because this is much smaller than most of the acoustical wavelengths that I'm emitting. Okay, so therefore it doesn't interfere with the acoustic wave. Now, if I'm strong enough, and I'm not, but if I'm strong enough to hold the table in front of me, right, it's going to be acoustically non-compact, and now you will hear a significant attenuation. Okay, so it means that for any case that is the case of a compact obstacle within a flow, if you work out the fact that your compactness is given by the Helmholtz number, so this Helmholtz number is like the diameter divided by the acoustical wavelength, and if you factor in the fact that the Strual number, FD over U, is typically of order 0.1 to 1. That's the order of magnitude for an obstacle in a flow. For a cylinder, it's Strual 0.2. If you take a square cross section, it's going to be 0.14, depending on the angle of the thing to the flow. But the order of magnitude is usually that. Then it means that the Helmholtz number can be written as 2 pi Strual times the Mach number. And therefore, it suffices for the Mach number to be small, for the Helmholtz to be small, because the Strual is bounded and usually a small value. Okay, so it means why usually obstacles in a low Mach number flows yield sources that are acoustically compact, and then the thing is acoustically transparent. Therefore, there's no significant acoustic scattering by the body in here, and therefore it's okay to use an incompressible flow solver that will neglect the acoustic perturbations here because the acoustic perturbations were irrelevant in the first place. Okay, so Kerr's analogy is a very nice framework. It gives you a very neat expression, and we will comment on the advantages in 1 second. The only thing is that beware that depending on which flow solution you use, you might have some problems if you are working with non-compact surfaces. Okay, so I'm going to give an example of. Yep.
How do you choose F? One number expression when you say it's this other way.
Yeah, you're right. That's the one of a dominant vortex tuning. I mean, for the von Karman street that develops over there.
Part of the spectrum.
Yeah, that's it. So the peak. But it's true that the argument fails if you look at the broadband high frequency component. The broadband high frequency component, but then you are talking about short wavelengths, and then the argument fails completely. Okay, so I'm really talking about the most energetic part of the spectrum. Right. So Kerr's analogy is overall only good news. Why do I mean that it's only good news? Because if you look at the order of magnitude of the sound field, sound intensity, the acoustic intensity radiated by this guy, which is the quadrupoles in the wave, and by this guy, this one radiates as Mach to the power 8. That was a light fields celebrated Mach to the power 8 low for jet noise. And if you look at the dipolar, it goes as Mach to the power 6. So it means that at low Mach numbers, this one will dominate. Okay? So the ratio is Mach to the square. So, and many industrial applications, landing of an aircraft, high-speed trains, automotive applications. So many applications are dealing with low Mach number flows. And it means that this guy in here, that is extremely expensive to calculate and very sensitive to numerical artifacts. I mean, for the quadrupolar contribution is usually a very, well, it's a diva. If you don't treat it with the best care, usually for the spurious numerical errors are going to scream louder than what you are looking for. It's negligible compared to this one because this is a tensor, so a rho0 ui uj, it's a tensor, so it's 6 components that you need to integrate in a volume. So it means something that can climb up to terabytes of data if you want to have a good prediction. This one is a scalar integrated over a surface, so a couple of gigabytes usually does a good job. So that's extremely good news in terms of data handling and, let's say, ease of the process. But the argument is only valid for compact sources. So if it's non-compact, but then you need to pay the price of a compressible simulation that needs to be very accurate to capture the acoustic perturbations. And that's different. Maybe I'll switch over this one. So that's an example of non-compact case. So we can come back to this if you have a question. That's one of the pathological effects or pathological cases for the application of Kerr's analogy. There's the case of the boundary layer, turbulent boundary layer over an infinite flat plate, for which you can easily demonstrate that the quadrupoles are really not negligible compared to the dipoles. Okay, so I'll skip to this. Maybe to go quickly to the acoustic energy equation, because then I can play with the toy over there. That's funnier. Maria has already entertained you about the ray tube, I believe, right? Maybe not all. Well, so for some it might be a review, and for others it might be news. So just a quick word about because it's part of an introduction to acoustics, the story about acoustic energy and intensity. So why are we interested in acoustic energy? Is because it allows us to make some balance of acoustic energy. And if the balance of the acoustic energy radiated outwards of a system is positive, it means that acoustic energy is produced by this source. If the balance is negative, it means that it's absorbed acoustic energy. Okay, and it's very convenient also to establish whether a system is going to resonate or not. So this acoustic energy equation is very convenient for this, and it will lead to the Rayleigh criterion that you will possibly have seen already, which is a criterion for thermoacoustic instabilities. So how do you build an acoustic energy equation? We take the same equation as before, linearize continuity, linearize momentum, multiply the first one by P prime by O0, scalar product the second one by V prime. We stir together and we have an equation that looks like this. Okay, so I'm now going to regroup the terms. So what do I have in here? I have something that smells terribly like an energy. Okay, 1/2 rho v squared. I mean, it smells a little bit like a kinetic energy. And then you have something that is associated with a compressive energy. So that's the amount of energy you store in a spring when you compress. And this translates in how the balance that you have when an acoustic wave is propagating from one particle to another. You have to see the air particles as small springs, attached to each other. And the acoustic wave progresses by storing energy in the spring, releasing it, giving momentum or kinetic energy to the next one, and so on and so forth. Okay. So that's the total acoustic energy associated with a wave. You have an acoustical intensity, so that's a flux of energy, because we have a divergence of something, and you know that when you will integrate, it will look like a flux. And then you have the amount of energy that is produced by your sources. Okay, and where here I've simplified a little bit the discussion by retaining only the monopole corresponding to the volume injection and the dipole corresponding to the unsteady forces. Yeah, I'm going to go back to this quotient a bit later. So as I mentioned, we like to make balance equations. So what we do, we integrate this equation over a certain control volume, and we integrate over a certain amount of time. Okay, so that's the same expression we had before. That's the amount of energy produced in the volume by your sources. And then it's very convenient, in particular when you look at occurrence of resonances, to look at a time harmonic problem. Because if a resonance occurs, usually your system will resonate at very well-defined frequencies. So then you can do this integral over one cycle of the oscillation. Okay, so that's 2 pi divided by omega. And what this gives is that the amount of power, so this notation in here, this opening things, there it means cycle integral. So whenever you see this, you must understand integral from 0 to 2 pi or omega dt. Okay, just to lighten a little bit the notations. It means that the amount of power that is radiated outside of your system, so the amount of acoustic energy that is radiated outside of your system, must be equal in a harmonic system, must be equal to the amount of acoustic energy that was produced by the source over this cycle. Because the problem is harmonic, it means it's periodic, so it means that the amount of energy you have at the end of the cycle must be equal to the amount of energy you have at the beginning of the cycle. Okay, so it means that all in all, everything that was produced must have evacuated. Right. Now, well, okay, this one is funnier. Now, what does this mean? Is that it tells you already a lot about the mechanism of the ray cube. For resonance to occur in a ray cube, you agree that you must have some net production of acoustic energy. Okay, the ray cube, you hear it because some noise is escaping the system. Now you can use this equation that you have in here to predict whether this integral in here is positive. If it is positive, it produces acoustic energy. If it is not, it's not produced. So first question, for the case of the ray cube, you know what the ray cube is? Yes, Paul? No? Not everybody. Miko doesn't know, so I have to explain. So the ray cube is something like this. It's a pipe, a glass pipe, with a metallic grid in here that is placed at a certain location. And if I heat up the grid, it's now that I'm testing the alarm system of Siemens. So nice when it works, huh? Okay, so it resonates, obviously. Now, what is the mechanism? That's a coupling. I'm not going to have the time to dig deep into the mechanism, but the physical mechanism that is taking place in here is that you have a coupling between the acoustic mode. So you hear a very distinct tone, right? That's obvious. So it means that there must be an acoustic resonator somewhere, and the resonator is a pipe, an open pipe. You know this as an organ pipe, maybe. Okay. So the organ pipe, you have boundary conditions, pressure fluctuation 0 here. Pressure fluctuation 0 here, because basically you are at the atmosphere. So you know that the modes are going to look like half wavelength sine waves and multiples of half wavelength. So the first mode is looking like this for the pressure, the next one will look like this, and so on and so forth. As long as you respect P prime equals 0 at the boundaries, it's a mode of your pipe. We are going to look at the first mode. Okay. So you have a resonator, you have a pure tone. Okay, now what is the source? The source is heat transfer, as you might have guessed, right? I'm heating up something, so obviously. So you have heat transfer, and the heat transfer is, there is a steady component that is associated to the natural convection that is established along the pipe. So I'm heating the thing in here, so it's like a chimney. Okay, there is a natural convection, but this natural convection must be modulated to be a source. And how is it modulated? It's modulated by the acoustic field. Because if your pressure field is pulsating inside of the pipe, you have a certain velocity field that is also pulsating in the pipe. And this small acoustic perturbation is superimposed to the mean natural convection velocity to modulate the amount of heat that is extracted from the grid to the fluid. Okay? And then the thing resonates as long as the grid is hotter than the surrounding air, and then eventually it decays. This one doesn't decay because there is a big fat electrical supply with it that we will hear in 1 second. So you have a source mechanism that is a modulated heat transfer. Now, modulated transfer, what kind of source is that? Monopole, dipole, quadrupole? Monopole, because there's entropy fluctuation, right? We have seen this. You have a strong entropy fluctuation due to the amount of heat that is extracted in an unsteady fashion around the grid. So we have to look at the monopole. Okay, so the monopole in the game here is this one. Okay, so that's the QM over rho 0, that's the volume injection that I have. And remember, the physics of the thing is that when you have an increase of heat transfer, when you have an increase of velocity, so when the acoustic field is going in the same direction as the mean advection velocity, you increase the amount of heat that you extract from the grid. Right? If you blow harder on something hot, you extract more heat from the something. And then you have a decrease of heat transfer when the acoustic field is going in opposite direction than the mean advection velocity. Right? So the thing then is to look at, okay, what is the amplitude of my source? And how is it phased with the acoustic pressure field? Because this is a cycle integral. Okay, so you must calculate the net amount that this quantity will have in the year over a certain amount of time. So first observation is that your monopole must be located at a portion of the acoustic field where the pressure fluctuations are significant. Okay, if you put the grid at this extremity or this extremity, it will never resonate. Because there we have a node of acoustic pressure. So if you put the grid here or there, it will never resonate. But the maximum of pressure fluctuation is in the pipe. So you must see the first resonant mode of the pipe as a kind of spring that you compress in each band. Okay? When you have a maximum of pressure in here, because the tube has ingested air from both sides, and it ingests air from both sides until a certain point where you have a maximum compression inside of the pipe, and then the spring bounces back, and you have the pipe is breathing air out of the pipe through both directions. Okay. So by this argument, you will say that if I place my monopole at the location where the pressure is maximum, I should have maximum effect. But if you put it here, what is happening in here? In the pipe, you have a maximum of pressure fluctuations, but what about the monopole itself? You have a node of velocity. Because in this scenario where the air is breathing in and out, this is always a stagnation point. Okay? So it means that you have no chance to modulate the heat transfer if you place the grid in the middle. Okay? So you must first have a source, and you make sure that you have a source by placing the grid at location where you have some acoustic velocity and effectively modulate the amount of heat transfer. And then you allow this source to produce acoustic energy by putting it at a location where the pressure field is not zero. Okay? So you see, with this simple equation, you can already tell a lot about the necessary conditions for resonance. So that's the situation we have here. We have the grid in here. We have the mean advection velocity. We have the small acoustic modulation around the grid. And we have the modes for the acoustic velocity with the nodes, pressure node, velocity node in the center. And then we have the mode for the acoustic pressure. The thing that is happening is that now you must make sure that the integral is positive. You know, you want the cycle integral of E prime, but you want this in here to be positive, to have a net production of acoustic energy. So for this positive, it means that you would like to have E prime and the heat transfer, the added heat transfer, more or less in phase. The problem is that it's not guaranteed. And this depends on the location of the grid. I'm finishing in 3 minutes. To have this phase, this phasing of the monopole with the grid, 5 minutes. Monopole in phase with so the monopole in phase with the thing, you count actually on the time lag. So this is the in time now. This is the acoustic velocity field. This is the acoustic pressure field, okay, at the location of the grid. And the thing that is working out is because you have actually a certain time lag between the modulation of the acoustic velocity and the heat transfer. Because your thermal boundary layer needs a little time to adjust. If I enter into the details, the year will kill me. So bear with me, there is a time lag in the system. And the time lag is actually bringing this heat transfer with a certain time delay with respect to the velocity, and this brings it in phase with P prime. And that's what you need. And that's the reason why this is working. So that's the reason why this is working. So same thing, but now with a little bit more punchy amount of energy. Just to heat up a bit. So, same story. You have the grid that is roughly at a quarter of the height of the pipe, and if you let it resonate, the thing that is interesting also is to listen to the rate of climb, to the rate of increase of the. You see, it's a relatively exponential thing. Now, if you place the grid at another location that respects all conditions we have seen so far, non-zero pressure field, non-zero acoustic velocity field, you will see that it's not going to resonate because now this time, by the same argument, the heat transfer and the pressure are in phase opposition. So let me try to do this. First thing you will hear that you will hear the difference of a wavelength. You will hear a detuning of the frequency because I will lengthen the resonator. You hear the frequency that is decreasing because of.
Now you have a grid in the middle.
Now you have a grid in the middle. So where you have a velocity node. So the source is 0. Okay. And now you have the situation where it's like this, like on the board. And effectively it's non-resonating. Because this is a phase opposition with the close. Now there is one way to make it resonate. And there's one Karman offered, triple Karman, very good Belgian beer, offered, or Westmalle. I don't do Karman or Westmalle, I'm talking about good beers. So that is offered for one of you who can make it resonate in this configuration. And now all of a sudden I'm not too late, huh? Change something. So there's a way to make it resonate without touching it. Sorry? It's not going to work. Well, I could, but it's super heavy and I'm not going to do it, but I can promise it's not going to work.
You don't touch.
You don't touch it. You can come.
Blow on it? Does that have? Blow on it from the top, give it some air from the top.
Try. Try.
Will it work?
But if you don't drink beer, we can find other compensation. No, come. So there's a way to make it resonate.
Without touching.
Without touching.
Okay. So it's over here right now. Kinda, right?
Yeah, kind of.
But I'm not allowed to do that?
Try again. Yeah, you can.
You
A
can't.
little bit, not too much.
The idea is good.
Maybe
What's
somebody else.
not correct? Do you want to try?
Probably changing in boundary condition,
No.
as you said.
Now, No, it's not this.
Blow from below. Just try it.
No, just try. You want to try?
Rather than blowing vertically, you will blow horizontally.
It's a different mechanism then. Then
You
it's
can try that also.
you can try. It might work for the wrong reason. It wouldn't be the first time that the right result is obtained for the wrong reason.
With the hair dryer, you can change the speed of sound in the.
Yeah, but the hair dryer you are probably going to quench the heat. There's something, there's a start of a didgeridoo kind of sound.
Somebody else?
That was a good attempt. Anybody else? Manas were on the right track.
Yeah, okay.
It's the intense, but there was too much enthusiasm.
There's also a bit of a cold, so I don't like it.
No? No other? Karman or Westmalan? Well, we're talking
Do I
business
get
here.
half a beer for being on the right track?
Sorry? You are on the right track.
Do I get half a beer for being on the right track?
You don't drink half
Can
of
you
Westmalan.
can you blow from the other side?
You can try.
You can try.
No, that's not difficult.
It's slightly more acrobatic, but.
Just do.
If we heat the outer surface, then it changes.
No. It's too complicated. No, the thing to blow with a hair dryer, you were the quench the heat transfer, because then you reduce the temperature difference between the flow and the thing, and you reduce the heat transfer.
Added another key.
No.
You can create like a.
Can you modulate the electricity so that?
No, I cannot do this. And this box is already archaic enough that I don't want. I mean, we are already that close from setting fire.
Can we put a source of sound?
No,
Just,
I'm-
try.
just try.
If everybody tries, just try.
By accident, I mean, science. The story of science is paved with yeah.
Like,
Yeah, come. And yeah,
because like, if you put like a boundary condition that is like acoustically closed,
Yeah,
No.
but
but
the
the
air-
cost structure, we can do it.
yeah, that's okay.
No, but this.
Remember, you need some heat transfer.
Yeah.
Right? So if you block the thing, there's no heat transfer anymore. So you need.
Just
But
try.
I want to
No.
change
On a presque.
What happens if we?
Yeah, try again. But you might have to remove the mask.
whether that.
There was something
Yeah.
less strong. Too strong. Too strong. Blow. Less hard.
So maybe introducing a vacuum, would that help?
Vacuum
Like
movie.
a reverse flow, basically. No.
You would do it. No, too strong. Sounds like cheating.
I do.
Well, I think we need to wrap it up because because the canteen will close, so we're not too far. Just need, remember the mechanism is this heat transfer, and that at a certain, you get it. The beer is for you. Wow. Remember, the way you reestablish the same situation is by having the flow in the same direction than in the initial thing, but you need to have the right time delay, and the time delay is a question of boundary layer thickness. So you need to blow at the same velocity as the one that you have with natural convection. You need to mimic the natural convection, basically. And if you are able to replicate the same tiny velocity, I don't know, there must be a couple of maybe 10 centimeters per second, maybe, I don't know really, but or even less probably.
But then in the end, like you close that.
No, but then it's the same. Then you go back, but then you look at this slide and you flip it upside down. Then you have again the velocity, the convection velocity now, and that is the right distribution. So I think we have to go. So I'll leave the summary on the screen if you want to read it. Otherwise, I think if you want to eat, we have to go. Right, Marie? So sorry for having been too long. But, thanks for your attention. I'm staying the afternoon and probably tomorrow, so we can discuss anytime.
Thank you, Christophe.